Hello, everybody. I'm Rich Ottinger, Marketing Programs Manager for Park Systems, and I wanted to welcome you all to Park Systems 2019 Material Science Research and AFM first webinar session titled Nanostructured Polymer Brushes with AFM. The presentation should be about 40 to 45 minutes, which should leave us some time for a Q&A at the end. You can use the raise your hand button on your control panel at that time, and I will try to unmute you so you can ask your question. If you prefer, anytime during the webinar, you can type in a question in that control panel as well, and I'll try to curate those at the end of the session. If we don't get enough time to get to all your questions, we will try to follow up on any of them with an email after the fact. It is now my pleasure to introduce to you Dr. Rigoberto Advincula. Dr. Advincula is Professor of Macromolecular Science and Engineering at Case Western Reserve University and Editor-in-Chief at MRS Communications. He is a Fellow of the American Chemical Society and a Humboldt Fellow, among many other professional awards, has published more than 250 peer-reviewed publications, and of particular note for today's topic is the co-editor of the book, Polymer Brushes, Synthesis, Characterization, and Applications. Please welcome Dr. Rigoberto Advincula.
Well, thank you, Richard. Thank you for the generous introduction. I would like to say good morning, good afternoon, good evening to all our listeners and viewers. I will be giving a talk today about nanostructured polymer brushes and AFM. First, I'd like to thank Park Systems for hosting this series, and I will describe to you later what's in store for the rest of the year in terms of these material series that we have created. So I'm with Case Western Reserve University. I'm a professor at Macromolecular Science and Engineering, and Case Western Reserve University is in Cleveland, Ohio, major comprehensive research university, and a very cultural center in the States, where we have the Cleveland Museum of Art, Cleveland Orchestra, and of course we are near Lake Erie. We are also home of the Think Box, one of the first makerspace laboratories and facilities for 3D printing and rapid prototyping and additive manufacturing. Here's a picture of the Macromolecular Science Engineering building, some members of my group, and I'd be happy to welcome you when you have the opportunity to visit Case. So my background is that I do a lot of research on interfacial chemistry, macromolecular science, polymer materials, patterning, nanopatterning, and even applications related to 3D printing and oil and gas. But today I'm going to focus to you about our work on polymer brushes and in general a very good introduction on what a polymer brush is and methods for grafting polymers at interfaces and surfaces. So what is the importance of a polymer coating, polymer film or ultrathin film? Well, it serves a function in that it preserves or protects the bulk material from the environment. Actually, it's a two-way street in that the environment actually is protected from the contents of the bulk material, in which case we sometimes label that as a packaging function. Nevertheless, this function can be done by a thick paint coating or protective coating or a very, very ultra-thin film, sometimes in the range of a few nanometers, which can have very interesting function as far as the environment and the bulk material is concerned. We sometimes label them smart coatings or nano coatings. And nano coatings can have different properties in terms of anti-fouling, optically active materials, color shifting, conductive, corrosion sensing, or applications in flexible electronics, etc. There are many types of applications that are being looked at in terms of these interesting materials. They can be used as anti-scratch resistance materials, biomedical applications, anti-fouling, or modification of biomedical implants as well. In the area of ultra-thin film, which we then call nanostructured ultra-thin film coatings, because we can make this order as up to a sub 1 nanometer order, where we can use alternating layers or depositions or multi-layer assemblies to make these ultra-thin films. For example, we call the adsorption of chemically labile additives capable of chemisorption, or we can deposit surfactants at the air-water interface using Lamier-Blodgett film techniques. What we have done a lot in the past is to use polyelectrolytes and other types of charged particles or polymers that are capable of forming layer by layer interfacial structures. One can also deposit them through vacuum deposition methods, vapor deposition, chemical vapor, or physical vapor deposition. And of course, to differentiate this from other methods, which I call bulk thin films, these are usually nanostructured multilayers that have the order of 1 nanometer or undulation of that order. So to differentiate the rest of these ultra-thin film methods, we are going to focus today more specifically about polymer brushes. So what is a polymer brush? Well, by definition, we can say that a polymer brush is a polymer chain that is tethered to a surface or interface with sufficient surface density such that the polymer chains are forced to stretch away from the surface to avoid crowding. This can also be represented by a grafting density that is much smaller than the radius of gyration. So the term polymer brush, of course, is analogous to a brush where you have extended bristles or chain. But in this case, we're talking about the macromolecular level. And there are a number of methods for tethering polymers on surfaces. We can simply classify them as a physical or a chemical adsorption method. Later on, I'm going to distinguish 3 other types of grafting methods: grafting from, grafting onto, and grafting through, which can have consequences on the density of a grafted polymer system on a surface. So what we label physical adsorption means that you have an interfacial boundary where a block of polymer or surfactant is distributed between this boundary of 2 phases. It can be achieved thermally or solvolytically. However, these are initially non-equilibrium phases, which then equilibrates over time. One of the consequences here is that since they are not a chemical boundary or relies on the ordering at the interface with equilibrium, they do not easily achieve very high grafting densities. On the other hand, what we call chemical adsorption usually results in a covalent bond formation or tethering chemistry, which can be achieved by let's say silane chemistry or phosphonic phosphoric acid chemistry on metals or oxides, or the interaction of thiol on gold. And this means that the adsorption can be achieved at a boundary, a surface, or an interface where this chemical adsorption or chemical interaction takes place. Now, let us try to distinguish grafting methods based on either physisorption or chemisorption. Whereas we can call a grafting onto approach, where we have a existing polymer chain with a group that is chemically or physically bound to a surface, we simply call that a grafting onto approach. Where we do polymerization such that the initiation takes place in the bulk, and during polymerization, it stitches through or grafts through surface-bound monomer species, then we have a grafting through process. However, what perhaps enables the formation of high grafting density chains better than the first 2 is what we call a grafting from method, or surface-initiated polymerization method. What is surface-initiated polymerization? It represents a grafting, as I mentioned, wherein the grafting point is much less than the radius of gyration. This simply means that an initiator in an addition polymerization method, typically, like free radical, ATRP, RAF, cationic, anionic, or metathesis polymerization, originates from the surface. In other words, the initiator is bound on the surface, and the monomer is limited by its diffusion to the surface, and hence it affects the polymerization kinetics dramatically. Now, this can be done on a flat surface, a colloidal particle surface, or other types of interfacial boundaries. So here's a general strategy for surface-initiated polymerization. The initiator is first immobilized on the surface. After immobilization of the initiator with a specific density, then polymerization takes place. Polymerization takes place where you have the active monomer diffusing to the surface. And then as the polymer grows, there's crowding out of the interface. And hence, one of the challenges of a grafting from technique is actually diffusion of the monomer and the crowding out of the interface or surface, hence sometimes leading to inefficiency or non-initiation of the surface-bound initiators. Now, this typically shows you some differences from the grafting to or grafting from. In a grafting onto method, the polymer approaches from the bulk interface or solution, which can be achieved by physisorption or chemisorption method, of course. That means that the pre-existing polymer with its given molecular weight, polydispersity, and availability of the reactive group or physically absorbing group has to find its way at the interface. Hence, some of the challenges of a grafting onto or to approach is that of achieving a very high grafting density. And it is also, of course, related to the different regimes by which a polymer or a grafted polymer falls onto in its certain stages of equilibrium. So we are able to, for example, differentiate different regimes of a polymer. Limiting case, of course, is a very high grafting regime. Another is a very loose regime, and in between we have other types of cases. So the tethered chains can have a critical grafting density, and the chains having a grafting density can be forced to stretch depending on the temperature as well as the solvent regime conditions, or what we call compressed and uncompressed brush. Sometimes this can be best characterized by plotting the grafting density and the height of the brush, which can be observed, for example, with techniques like X-ray reflectometry or ellipsometry. So typically, you will have regimes which is sometimes called just a mushroom regime, a pancake regime, and a brush regime. The segment density profiles for each regime is shown here, where you have the differentiation between the height and the density on the surface. So let's talk about now the influence of solvent swelling, phase immiscibility, and wetting. So we can measure the grafting density as a function of solvent quality, brush height, and radius of gyration, all terms that can be characterized with techniques like ellipsometry, X-ray reflectometry, quartz crystal microbalance, and of course, atomic force microscopy. The importance of the equilibrium, thermodynamic equilibrium, can be matched by the ability of this polymer brush to swell selectively depending on the solvent quality or theta condition. So for example, the different types of solvents, let's say in a mixed brush regime as shown here, can resolve in a variety of morphologies and even wetting conditions that are limited by the last solvent to which a material is exposed. So a polymer brush, for example, can be in the case of a mixed polymer brush or a block of polymer brush that is tethered to a surface. And we'll see several examples of this. Here is one interesting example which shows that the micromechanical and lubrication properties of a surface can be changed as well by the condition as well as the patterning on a surface. So what we have here is basically a polymer in which we have different charge densities and regime. Depending on the type of solvent, it will have a variety of friction force properties on a surface. Dry state or swollen state, for example, can cause changes on the height of these polymer brushes and hence affect some of its wetting behavior. Just to emphasize this fact, let's say a very well-known lotus effect in nature that is copied on surfaces can, of course, affect the wetting behavior of a tethered polymer system or the morphology of a particular thin film, as well as the formation of different types of lithographically bound surfaces, and hence the wetting behavior. So most of this is in fact characterized by the Cassie-Baxter phenomena. Now, another example here is that a polymer surface can also have an electro-optical function. Here is the case of a polymer brush which contains a whole transport material such as this triphenylamine, affecting the bulk heterojunction properties of a polythiophene and a cadmium selenide nanoparticle on a heterojunction device. So in this case, the structure of the polymer brush has a big influence on the whole mobility or transport of these charge carriers at interfaces, hence affecting its performance, let's say, as a photovoltaic diode. So these examples I've shown you, a few examples, are some of the peculiar uses of a well-defined polymer brush, whether it's at the interface, an electrode surface, or controlled wetting behavior. So let's talk more now about our work on polymer brushes. So back in 2006, we actually published one of the first books on grafting polymer brushes, and monographs as well has appeared. This technology is about 25 years old in terms of its potential uses in fields like electronic devices, wetting, packaging, and biomedical applications. So what I would like to emphasize are some of the chemistries that we've developed through the years involving that of polymer brushes based on surfaces. So we were one of the first to pioneer what we call anionic polymerization. Anionic polymerization on surfaces. We call this the LASIK technique. One technique that we used involved the tethering of diphenylethylene co-initiators, which were then activated by N-butyllithium. The anion generated allows us to, for example, polymerize styrene, or even form a block of polymer brush with isoprene. Hence, in a classical anionic polymerization, which is done in solution, we're able to do it on surfaces. And in this case, a modified gold surface with a diphenylethylene co-initiator. So some of this early work resulted in the following. We were able to control the grafting of these polymers actually on silicon wafer and gold surfaces as well. This was done by using N-butyllithium on the diphenylethylene initiator. And for example, the left AFM picture shows the grafting on a silicon wafer surface, and the right one on a gold wafer, gold-coated wafer, which actually showed a thicker brush of about 23 nanometers versus 14.7. And here we use, for example, X-ray photoelectron spectroscopy to verify the presence of grafted polymer, in this case polystyrene, on a silicon wafer. So you can see the silicon and oxygen peaks on the binding energy associated with these elements. And on the right, we have a gold-coated substrate, which verified again the grafting of the polystyrene on a gold wafer surface. So moving to block of polymer strategies, as I mentioned, we were able to graft polystyrene and then followed by a grafting of isoprene. Since this is a living polymerization, anionic polymerization, after depleting all the styrene monomers, we simply add in the isoprene monomer to produce this block of polymers. Not only with isoprene, we were able to achieve this with blocks of polystyrene and polyethylene oxide and polyisoprene and PMMA. And here are several examples of how we've done it in terms of grafting these copolymers. Now, one of the peculiar things that we notice with anionic polymerization on surfaces or interfaces is that they typically do not have very high molecular weights, or they do not correspond sometimes to the predicted monomer feed ratios. And one of the reasons which was outlined in our previous publications is that the surfaces actually are not ideal in terms of the kinetics of this interface. Plus, they actually have inefficiencies like what I mentioned based on steric crowding of the surfaces as the monomer diffuses through the interface. And lastly, some of these surfaces can actually be classified as impurities, hence limiting some of the correspondence between the monomer feed ratio and the expected thickness of these brushes. And I'll show you several peculiar examples where we've used this in a number of practical applications. But first, just to emphasize that what we can do on a flat surface, we can do on a particle interface as well. Particle polymerization simply means that the grafting is done, again, by tethering the initiator on the particle with a number of strategies outlined earlier, chemisorption or even physisorption, and then followed by the polymerization on the particle. So what happens is we achieve a core shell geometry where the core is the particle substrate and the shell is the grafted polymer brush. Here's an example of how we have achieved anionic polymerization of polystyrene on a silica nanoparticle. We use silica nanoparticles of the order of 12 to 20 nanometers in diameter. After fixing the diphenylethylene co-initiator, we then activated these particles by adding N-butyllithium. This was done using high vacuum techniques or simply inner atmosphere, where we were able to introduce the initiator, the monomer, through this glass reactor by breaking the seal. So this is a very classical anionic polymerization procedure. The result is we were able to graft the polymer on clay or silica gel or any particle that is introduced in this reaction chamber. What we will do in a typical procedure is actually to characterize the grafted polymer using SEC. So for example, if we use silica particle as a substrate, we will then mix it with potassium hydroxide alcohol to remove the bound polymer. The bound polymer can then be characterized normally by GPC. What we found actually on these LASIK procedures is that we were able to get a good correspondence of the monomer styrene feed ratio with the molecular weight of the polymer. Hence, we actually achieve here a type of living polymerization. However, not the exact monomer feed ratio, but in terms of the linearity of the process, it is well taken. Here, for example, you can see a comparison between a free polymer with a monodispersed Gaussian distribution, or I'm sorry, a Poisson distribution versus polymer that we actually grafted on the surface of silica particle. So what you can see here, and this is a very typical behavior, is that we have very broad distribution or broader distribution with polymers grafted by anionic polymerization on surfaces. We have done this on clay nanoparticles. So we modified clay with a cation diphenyl initiator, activated it with N-butyl lithium. Here is an atomic force microscope of the clay nanoparticles that we modified. So what's interesting with clay is that, of course, it is hygroscopic, and therefore, by heating it up and drying it at 120 degrees Celsius, which is a very important procedure, we were able to do anionic polymerization on clay with those cationic bound surface initiator. Characterization can be done by infrared spectroscopy, both for the polymer bound on the clay or separately from the polymer after it's degrafted. And interestingly, since the polymerization is followed by the intercalation and delamination of the clay platelets, then we can also observe the changes that are happening on the spacing between each of those clay platelets by X-ray diffraction. Now let me switch to free radical polymerization in this case, where we have utilized initiators, AIB and like initiators as shown here, and then grafted them on the surface and did the polymerization at the same time. Now this particular design, we have an AIB and like initiator with two quaternary amine groups. These were inserted on the nanoclays, and during the polymerization, they actually also produce delamination. And again, we follow this by infrared spectroscopy, X-ray, and also thermogravimetric analysis. The bottom line is that the grafting or free radical polymerization, grafting of polymers on clay nanoparticles can be easily achieved by these procedures. One of the ways that we prove this can be done on a clay is that we are able to produce very monodispersed systems, let's say with this particular design. So in this case, we have a monocationic design which we inserted in clay. The difference is that in this particular experiment with PMMA, we actually achieved low polydispersity or a good polydispersity with the different reactions conditions that we did with PMMA on clay. So to our surprise, these are very good systems that confine polymerization, resulting in low polydispersities. Here is a polymer brush grafting where we actually observe the nanoclay surface by atomic force microscopy after the polymer has been grafted directly on the nanoclay. So this was verified by this AFM image, as well as the X-ray, XPS, and a technique called surface Plasmon resonance spectroscopy that shows the change in morphology after the grafting of the polymer on the surface. So to switch back, this is the nanoclay platelets before polymerization, and after polymerization, you can see the change in morphology. So atomic force microscopy here is a critical technique for characterizing the morphology change on the nanoclay surface. Now, Let's look at some of our work on functional and responsive polymer brushes by combination with layer by layer polyelectrolyte macro initiators. So as I mentioned, the use of polyelectrolytes to modify surfaces with charged particles or polyelectrolytes can be achieved by alternating the deposition of, let's say, a negatively charged polyelectrolyte and a positively charged polyelectrolyte. These can be done on a flat surface or a particle surface, as shown here. One can achieve, in fact, a hollow shell configuration, let's say in this diagram, by removing the particle. And this has been done by many, many groups through the years and demonstrated in particles and surface substrates as well. We have done a lot of work in this field through the years. Here is a particular paper where we published the grafting of polymers on a polystyrene particle. The idea is to coat the colloidal particle with polyelectrolyte macroinitiators. The macroinitiators are then capable of polymerization, therefore resulting in a core shell particle with a polymer brush shell. And in principle, it's possible to get a hollow shell geometry, although this was achieved by other groups, wherein after grafting the polymer on the surface, one can digest or remove or simply dissolve the particle to produce this hollow shell. Here's an example of the procedure and the chemistry that we use. So for example, we synthesize these macroinitiators based on a modified polyacrylic acid. This is an initiator for ATRP, or we call this PAA-ATRP. We first deposited alternately a negatively charged polyacrylic acid and a positively charged PDADMA on a particle surface, and then grafted the initiator followed by polymerization. This is shown here in this experiment. So originally, these polystyrene particles of about 400 nanometer diameter were coated with the polyelectrolytes to produce a layer-by-layer shell. This was followed by the zeta potential, which indicated the deposition of the negatively charged and the positively charged polymers, followed by the grafting of the initiator. And we can also track this by TEM and FTIR as well. IR confirmed the presence of the macro initiator in the surface. This was then followed by polymerization of the corresponding polymethyl methacrylate. So here you can see the particles after grafting the polymers. The core is slightly visible on the surface, but then the surface was coated with PMMA. Again, to characterize this type of brushes, we would then degraft the polymer or dissolve the PS, and then we will characterize by NMR, GPC, or TGA. In fact, one of the consequences of using ATRP is sometimes we have polymers that are bound or not bound on the surface, which we can use also to characterize the efficiency of the ATRP. Okay, here's an example of what we call a dual responsive polymer brush. The stimuli responsiveness can come from either changing the pH or changing the temperature through the LCST behavior. Hence, to do this, we would need a weak polyelectrolyte interface and a LCST behaving polymer brush, in this case, which can be fulfilled by grafting poly-NiPAM. So the polyelectrolyte layers were first deposited with the pH responsiveness of polyacrylic acid and PEI, positive and negatively charged. But the last layer actually involved the grafting of these two ATRP initiator, a positive and a negatively charged initiator. Once we've grafted them on the surface, we will then grow the polymer brush, as shown here. So in principle, we have a pH responsive lower layer and a temperature responsive upper layer. So in this case, we can affect the changes either by changing the pH or the temperature. Such was demonstrated as shown here, where we get different swelling behavior as a function of pH. Low pH causes swelling, high pH causes contraction. On the other hand, low temperature produces wetting, and higher temperature above the LCST results in more hydrophobic behavior. We also observe this behavior by looking at the transport of molecular ion probes or electrochemistry by cyclic voltammetry through the surface. Again, by changing the pH and temperature, we can observe changes on the voltammogram, indicating the change in current density versus potential for each of these different conditions. Okay, with the remaining time, I would like to focus on polymer brushes as applied to solid-state devices and polymer brushes patterned on interfaces using colloids and polymer grafting methods. So one of the interesting things with solid-state devices is, of course, trying to play an important role on the whole transport or even electron transport in devices such as LEDs and photovoltaic devices. And polymers play a very important role, whether it's the active material or the passive material. In this case, we have a surface, an indium tin oxide, with a rough surface that was modified by polyvinyl carbazole. Polyvinyl carbazole brush, which was polymerized using AIBN initiator grafted by silane chemistry on ITO, resulted in a homogeneous polymer brush coating on the ITO. Not only it improved the surface homogeneity as shown here by the AFM micrograph, it actually improved the device performance. So after cross-linking the vinyl carbazole units on the polymer brush, this resulted actually in a lower turn-on voltage as compared to a non-modified ITO surface for a device structure made up of PVK as a whole transport layer, polyfluorine as the active blue emitting polymer, and then aluminum as a cathode. So let me skip some of this slides to focus on patterning. So here is an example of how we have used the technique of electropolymerization to graft a raft initiator. RAF stands for reversible addition fragmentation chain transfer on a conducting surface. So polythiophene, for example, can be electropolymerized from the terthiophene monomer with a RAF chain transfer agent. Once we are able to graft this conducting polymer macro initiator on the surface, we can then polymerize, let's say, polymethyl methacrylate with the AIBN initiator, graft the polymethyl methacrylate, and since it's a living free radical initiation method, we can then graft a second monomer, in this case styrene. So in principle, you have a conducting polymer macro initiator layer followed by a polymer brush, a block of polymer brush of PMMA and polystyrene. Okay, so we were successful in doing this. Published several papers that demonstrated that the macro initiator, conducting polymer macro initiator, can be grafted by cyclic voltammetry. In fact, this can be done selectively as a pattern layer. Here we have a pattern surface where the conducting layer can be modified by this bifunctional electropolymerizable carbazole with a chain transfer agent on the conducting layer. We can grow one polymer brush of polystyrene on this conducting layer. But since the glass etch side can be modified by silane chemistry, we can actually graft by silane chemistry an ATRP initiator and grow another polymer, in this case poly-9PAM. Here's an example of this chemistry where we've actually first demonstrated the grafting of PMMA brush on an ATRP initiator. The image as shown here by IR imaging shows the image and the corresponding IR spectra for the carbonate stretching of PMMA, and also verified by atomic force microscopy in terms of this morphology. And again, XPS or X-ray photoelectron spectroscopy can be used to verify this grafting. Here is a binary composition of a polystyrene with a poly-9PAM brush grafted on the bare silicon layer. So initially, the blank pattern ITO looks like this. And then after grafting the two polymers, the SEM figure looks like this. Now, what's interesting is that this modification, of course, that does not reveal the chemistry. But what's more interesting is if you apply a technique called IR imaging, the image or morphology change on the brush can be distinguished by the IR spectra that we observe by IR AFM to that of the green color revealing that of the polystyrene grafted polymer, and then the blue color revealing that of the poly-9PAM. Hence, let's say a combination with AFM and IR microscopy, one can have a distinct characterization of both the morphology and the chemistry associated with the grafted polymer brush. So I'd like to do this last example by showing how we have patterned polymer brushes using colloidal templates. Back in 2011, we demonstrated that colloidal particles can be used to pattern surfaces where the colloidal particles can form a hexagonally packed structure as shown here. The interstitial spaces provides a way for electrode deposition, let's say, of a conducting polymer to be made on the electrode surface. Hence, by masking or using this as templates, one can observe the formation of arrays, as shown here. So these arrays are basically conducting polymers that were deposited at the interstitial spaces in between those of the particles, resulting in a honeycomb, half comb, or a full dome structure as shown here. And in fact, they can be harvested even as particles. So we have demonstrated that these conducting polymers can be grafted at the interface as shown here. However, since the holes of these arrays are basically exposed electrode surfaces, one can modify the surface to do polymer brush chemistry. And that's exactly what we've done on this work. We grafted an ATRP initiator in between those holes, and then we grafted or grew a poly-9PAM brush within those holes. And you can observe by the atomic force micrograph how the holes have been modified with the polymers in between. Now, a conducting AFM technique actually allows us to distinguish between the conducting polymer arrays and the non-conducting polymer brushes that were grafted on the surface, resulting in a difference in the color density or pulse color map, as well as differences in the heterojunction behavior. Now, here's an example where the macro initiator we use is also a electro depositable conducting polymer. In this case, instead of growing the brush inside those holes, we actually grow the polymer brush along the arrays. So in this case, after electrodepositing this macro initiator on the surface, the colloidal particles were then removed, revealing a macro initiator surface and then growing the polymer brush. We were able to demonstrate this with an ATRP, a wrap, and a metathesis system. And just to show you all three, we were able to do the grafted polymer system. You can see the change in morphology by AFM as we grow the polymer brushes along the ridges of the patterned array, not in the hole. On the other hand, since we are able to do hole, modify the hole with an initiator for ATRP, we can do a dual or binary composition in which the arrays are modified with a polymer brush, but then we can also modify the holes with another polymer brush having a binary composition. And in fact, we were able to characterize this based on the diffusion properties of, let's say, a molecular ion probe using cyclic voltammetry as a method to look at the diffusion of polymers on a conducting substrate. So believe it or not, time has lapsed and we're almost at the end. We'll be happy to answer any questions on this first seminar for the year in our Park AFM Materials webinar series. And with that, I'd like to thank you and I'll be happy to answer any questions.
Okay, so I've got a few questions that came in during the talk, and I'll start by asking those. But in the meantime, if anybody has a new question, feel free to raise your hand, and I'll be able to unmute you so you can ask your question. I'll start with the first one from Mahmoud Baniasadi. He wants to know how the friction was measured on AFM to compare the effect of various liquids.
Yes, we actually have a paper that we published in Langmuir. There are two modes. One, of course, you can use the friction mode or do a lateral force probe microscopy technique. Basically, you can drag the AFM tip on the surface and then measure the changes in the force potential or surface potential or surface force potential or simply surface forces based on the response of the tip on the surface. That's one experiment. The other is you can do a sort of a nano indentation experiment where you have tip retraction and probe going in and out of the surface, and again observe the changes in the surface forces. There are several publications on this, but sometimes what is important is to calibrate those type of measurements with a known method.
Okay, next question from the same questioner. Did you measure the hydrophobicity of these structures?
It's not possible to measure, quantify specific islands or domains with a AFM tip unless you have a very good correspondence with the surface energy between the tip and the morphology. However, what we will generally do on the pattern surface or simply the grafted surface is to do dynamic contact angle measurements. Although that is more general, yet it is revealing in terms of some of the surface energy and morphology of the surfaces. But it's possible, of course, to use atomic force microscopy. Again, you have a very good correspondence between the tip surface energy and the substrate, as well as a good calibration method.
Okay, and one more from the same participant. Did you try any piezoelectric polymer to create polymer nanobrush?
Good question. We haven't. It will be interesting to look at some materials, for example, with a piezoelectric behavior like PVDF or other types of charged polymers. What's interesting with AFM methodologies these days is you have a lot of options between the tip and the surface or different modes based on phase imaging, electrostatic, electrical, magnetic force microscopy, and other types of specialized surface probe microscopy methods.
All right, and I've got one more here from the attendee. His name is Eric Zeman. Besides morphology, would it be possible to establish brush surface density in AFM?
I would use AFM in combination with techniques like quartz crystal microbalance or even ellipsometry. So for example, it will be ideal to first measure the brush height, which is a variable for thickness. Then you would use, let's say, quartz crystal microbalance or even electrochemistry to look at the charge density as well as the swelling behavior of this material. So in other words, what would be good is always to have two techniques that can be used to verify or quantify the measurement. Unrelated techniques, by the way. So for example, we had a previously published paper where we used electrochemistry, PM, and ellipsometry. I don't think we used AFM at that time to verify the charge density. And then to confirm this on a particle surface, we actually did the same polymerization on a particle, and we used thermogravimetric analysis to confirm the surface grafting density. So my suggestion really is to use AFM with another technique to verify and correspond the two measurements, and you will have perhaps the opportunity to measure grafting density better.
Okay, and I've had one more come in, and this question is, did you explore the gas sensing application using these structures?
We have used them as sensors for determining not gases per se, CO2 or H2S or N2, but we actually use this for detecting, let's say, aromatic hydrocarbons, different types of gases based on hydrocarbon used in the oil field. What is possible is that you can use, let's say, again, a technique called quartz crystal microbalance or even surface plasmon resonance spectroscopy to monitor the changes in the mass or the dielectric properties, optical properties with swelling by gas. So yes, it's possible. Another idea would be, for example, to detect CO2 with amine-containing brushes and simply monitor it by UCM. So yes, it's possible to use polymer brushes for gas sensing.
All right, I haven't seen any more questions come in. We have one hand raised, so I will call on that person. All right, can you ask your question for Dr. Advincula?
Yes, how stable are these polymer brushes when you're doing cyclic voltammetry?
The cyclic voltammetry can be a function of the, of course, the maximum voltage, and sometimes the problem is not the brush per se, but the coated electrode itself. So, for example, if we do cyclic voltammetry with about 2 volts oxidation, we sometimes strip the gold. So as far as polymer brushes is concerned, if the chemistry is especially bound with covalent linkages, for example, silicon oxide modified with silane chemistry, which is better than thiol and gold, because thiol and gold can be affected by temperature as well. Usually, those are quite stable and are as stable as the oxidation or reduction waves are concerned, as long as you don't strip, let's say, the case of gold-coated slides beforehand. So I would say, in general, these polymer brushes are very stable for electrochemical experiments.
All right, I think that's all the questions that we've had. So I'm going to ask the final question, which is if you could give us a brief overview of next month's topic, new surfactant design.
Oh, yes, I'll be happy to give a brief introduction, Richard. And again, thank you for our listening audience and viewers of this series. Every month for this year, 2019, we have planned topics, and please feel free to visit the website. For next month, we'll be talking about new surfactant design. I'll be talking there about the basis and the origin for surfactant chemistry, the uses of typical parameters for designing surfactants, whether it's used as a viscoelastic surfactant, detergent, or in oilfield chemistry. It's very important to appreciate their behavior, not only as micelles, but their ability to extend their morphology as well as phase behavior in a variety of fluids. So I'm looking forward to giving this webinar next month.
Okay, so thank you very much, Dr. Advincula, for your time and for participating in this series with us. Again, next month's session will be on Wednesday, February 20th at noon Eastern Time, so please join us for that. I want to thank you all for attending today's session, and I hope to see you all at future sessions, as we have one per month, the third Wednesday of each month. For more information on Park Systems AFM, please visit parksystems.com. If you have any AFM related questions, you can email us at inquiry@parksystems.com. And if you have specific questions about the webinar series, please feel free to reach out to me directly. My email address is richard@parksystems.com. And thank you one more time for joining us for our first session of the 2019 series. And we hope to see you all next month. Take care.